So eta star is smaller than 1, and eta star is an upper bound. 1 minus 1 over n for every n. Because eta star is smaller than 1, 1 minus eta star is greater than 0. By necessity, there is an integer k such that 1 minus eta star is greater than 1 over k. Right? This is not equal to 0 because eta star is greater than 1. Why is that necessarily the case? Well, here's 0, here's 1 minus eta star. It is not equal to 0. And so by the Archimedean property, we can find a k such that 1 over k would fall here. Now let's rearrange the terms. You get 1 minus 1 over k greater than eta star, but that contradicts the fact that eta star was an upper bound of all the values 1 minus 1 over n. Here, we found a value of n, specifically k, given by the Archimedean property, for which 1 minus 1 over k is greater than the supposed upper bound. So if eta star is an upper bound, it cannot be strictly smaller than 1. It has to be equal or greater than 1. And we know that 1 is already an upper bound. There's only one possibility here. The supremum is equal to 1. If it was greater than 1, it would be larger than one of the upper bounds, which is itself the value 1. So this example is done with. Move on to the proof. Now the sequence xn is bounded above, so the range of values that the sequence can take is also bounded above. By the completeness of R, the supremum of the range of values exists. The only thing that remains to show here is that the supremum is in fact the limit of the sequence. How do we show something is the limit? We use the definition. Let epsilon be some positive number. By definition, x star minus epsilon is not an upper bound of the range of value the sequence can take. Otherwise, if it was an upper bound, given that it is smaller than x star, it would be the supremum, not x star, because x star is supposed to be the smallest upper bound. So if it's not an upper bound, there exists some integer, which we'll call n epsilon, to indicate that this integer depends on the value of epsilon that you selected, for which a value of the sequence resides between x star minus epsilon and x star. Right? If that wasn't the case, if you cannot find a value of the sequence in between these two values, what it means is that x star minus epsilon is an upper bound of the sequence. But we know that's impossible because the supremum is x star, not x star minus epsilon. So there's got to be at least one in between. While we're at it, x star is going to be smaller than x star plus epsilon, right? Because epsilon is strictly positive. Now what we do know is that the sequence is increasing. We haven't yet used that. So what this means is that for every index, every integer, n greater than n epsilon, the value of the sequence at n has to be greater than the value of the sequences n epsilon, because it is increasing. So graphically, where are we at? Here's your x star, here's your x star minus epsilon. We found that there was at least one value of the sequence between x star minus epsilon and x star. This might have been x and epsilon. And what we do know, because the sequence is increasing, is that every other point in the sequence after the n epsilon point has to be greater than n. In fact, we know a little bit more here, that sequentially they get larger. But we don't care about the sequence part here. We only care about the fact that they all have to be greater than x and epsilon whenever n is greater than n epsilon. Now what this really means is that What this really means is that for every epsilon greater than 0, there exists this n epsilon, which we found because x star minus epsilon was not an upper bound of the set of values the sequence can take, such that x star minus epsilon is going to be smaller than xn, and be smaller than x star plus epsilon for every value of n contained, for every value of n greater than n epsilon. And we know that this second inequality here holds because x star is an upper bound for the xn. Well, that's exactly the definition of the limit of the xn. Every increasing bounded above sequence converges to its supremum. Here's an interesting example. Let's define a sequence using a recurrence relation. The nth term of the sequence is going to be the square root of twice the n minus 1 term of the sequence. This can only be defined when n is greater than some value. In this case, we'll say 2, and we'll set the starting point of the sequence to be equal to 1. Does this sequence converge? And if it does converge, what is the limit? We can start playing with it. We know that x1 is equal to 2. Good. Sorry. We know that x1 is equal to 1. x2, by definition, would be the square root of twice x1, which in this case is 1. Square root of 2. Perfect. What would be x3? It would be the square root of twice x2. So twice the square root of 2. What would be x4? It would be the square root of twice x3, which we know to be the square root of 2 times the square root of 2. Okay, so these are my values. Does it converge? And if it converges, what is the limit? Well, we're going to use the theorem. First, we show that the sequence xn is increasing, and then we'll show that it is bounded, and then we'll know that it converges by the theorem on increasing bounded sequences. And finally, I'll compute the supremum, get the limit. Although, to be fair, there's a faster way to compute the limit. The theorem tells us that the limit is a supremum, but it would be sort of stupid to try to compute the supremum directly, given what these values here look like. Okay? How do we show that it is increasing? We need to show that xn is smaller than or equal to xn plus 1 for all n. This is something we do by induction. The base case, is it true that x1 is smaller than x2? Well, x1 is 1, x2 is square root of 2, that holds up. The next case is, let's assume that xk is smaller than xk plus 1, which is to say we assume that the square root of twice xk minus 1, which is exactly the value of xk, is smaller than the square root of twice xk. Can we from that show that xk plus 1 has to be smaller than or equal xk plus 2? Can we show from that that it must be the case then that the square root of twice xk will be smaller than the square root of twice xk plus 1? Well, if xk is smaller than or equal to xk plus 1, it's true that this means that the square root of twice xk minus 1 is smaller than or equal to the square root of twice xk, but it's not really important. It's not really useful for us to show what we do want to show. What we'll do instead is say, look, if xk is smaller than xk plus 1, then I know that twice xk is smaller than twice xk plus 1, and in particular, the square root of twice xk is smaller than the square root of twice xk plus 1, assuming that I'm taking the positive square root here, obviously. And while this is exactly xk plus 1 being smaller than xk plus 2, what it is that we wanted to show. So we've managed to show by induction that xn is smaller than xn plus 1 for every n, which is to say that the sequence is increasing. Now we'll show that it's bounded above. In fact, I'll show that it's bounded above by 2. How do I find this number? Well, I computed the numerical values of the first few functions, and it gave me the impression that nothing was ever bigger than 2. So let's see if it is indeed bounded above by 2. It is again a proof that we do by induction. As a base case, is it indeed the case that x1 is smaller than 2? Yeah, because x1 is equal to 2. And now what we want to show, the induction step, if xk is smaller than or equal to 2, can I show that xk plus 1 must be smaller than or equal to 2? That's pretty easy. If xk is smaller than or equal to 2, that means that twice xk is smaller than or equal to 4, meaning that the square root of twice xk would be smaller than or equal to the square root of 4. The square root of 4 is 2. Square root of twice xk is xk plus 1. And so I've managed to show that assuming that xk is smaller than or equal to 2, so must xk plus 1. So it's not just that these values here all look to be smaller than 2. I mean, if I look at them, if they all look to be smaller than 2, they will also all look to be smaller than 3. It's that I'm trying to find a value here for the bound, which I'm going to be able to use with the recurrence relation. Right? So there was a little bit of work done behind the scenes to come up with that real value. I could have picked a 3 as well, and we would have had a 6 here, and we would have ended up with the square root of 6, which, well, I guess is greater than 3, but that's not what we would have wanted, right? So I had to sort of fiddle around with this a bit until I found the right value. At any rate, xn is increasing, and now we've shown that xn is bounded. So now, what is the value? The theorem says that the value of the limit will be the supremum of these values, but it's pretty hard to compute the supremum given that we can't explicitly write any of these values. Instead, we'll notice the following. We know that xn is equal to the square root of twice xn minus 1, and we have shown, because the sequence is increasing and bounded, using the previous theorem, that the limit exists, that the sequence is convergent. So, I can actually write this here. This limit exists. It's got to be the same as the limit of the square root of twice xn minus 1. And because I know that this limit exists, let me call it here x star. I know that this limit here exists, meaning that I can use the operation, meaning that I can use the results on operations on limits. This will be the square root of twice the limit of xn minus 1 when n goes to infinity. But this is also x star, the limit of xn or the limit of xn minus 1 when n goes to infinity. You're interested in what's happening eventually. So you end up with twice x star. So whatever the limit x star is, it has to satisfy the relationship x star is equal to square root of twice x star. How do you write this out? It would be x star squared is equal to 2x star. And if you work it out, there's only two solutions. Either x star is equal to 0 or x star is equal to 2. It can't be equal to 0. Why can it not be equal to 0? Well, x1 is equal to 1, and this is an increasing sequence. So x star has to be greater than or equal to 1. So we're left with the limit here being equal to 2.